Yes, sir. Now I am okay. Yeah, please start.
Okay. Okay. So good evening, everybody. And to start with, I must thank ASM India chapter, as well as Mr. Sandeep, as well as Mr. Vivek, who invited me for this and gave me the opportunity to be with you. We often discuss heat treatment of various components. Gears is one of the most common component which is heat treated, and today we are trying to look at not just heat treatment per se, but also its relationship with the design aspects, the specifications, how they are laid down, all that. So next slide, please. Yeah. So here we can see typical life cycle of the component, that it is designed, then manufactured, heat treated, ground or finished in some way or the other. It is assembled, then it goes for usage in the field. If there is an issue or there is no issue, that feedback will come from the field, and if necessary, the corrections will be done to improve the performance. So that is the basic cycle of the life cycle of the component. Next slide, please. Yeah. So this is a typical picture which many of you must have seen in books related to gears. So it shows how stresses in gear tooth are concentrated at two major points. Number one is at the on the active profile, where the load or torque which is to be transmitted exerts a very high amount of stress compression on the surface while it is rolling. And the other one, on the loaded side, at the root fillet, there is a very high bending stress. On the other side, unloaded side of the gear tooth, you'll have compression at the root fillet. But these 2 points are very important for us to understand. Next, please. Yeah. So, because of this concentration of the stresses at two major points, there are two considerations in the design of gears. Number one is the contact stresses, because although on the component or gear face, gear tooth surface, you will find a sort of elliptical contact pattern. While it is in actual operation, every thin line is point of contact, and rather line of contact. And that single strip, very small strip, has to support the total load as well as the payload of the vehicle. So it's of very high value, the stress involved there, and that's why contact stress is one of the major factors in the design. The second one, naturally, is the bending stress at the root fillet. And because the gear tooth is a cantilever, the loaded side is very highly loaded at the root fillet, and that stress has to be looked at while designing the gear. It's to be noted that both these stresses are cyclic in nature. They start with a small value, go up and come down again. So these cyclical nature or Hertzian stresses, they are to be considered while designing the gear. Next, please. Next slide, please. Yeah. So typically, the metallurgical specification are given below, and one by one we'll see how they are related to the gear design. So surface hardness is the first and foremost. We, in fact, most of the gears, we say they are surface hardened, okay, by one method or the other. So typically 60 plus minus 2 HRC is specified, and it represents a strength which is more than 300 KSI, which is exceeding the requirements of the design for even the most heavily loaded gears. So surface hardness, uh, in fact, here I would like to mention that most of the design specifications like surface hardness and core hardness, in metallurgy we do not specify the things that we want. What is required is strength, okay, and what we specify as is hardness, which is which has got relation with the ultimate tensile strength. So in most of the metallurgical areas, it is like that. That requirement is something the specification calls something else, which can be easily measured on the shop floor as well as in the lab, and that can be correlated to the design requirements. So next is of course effective case depth, which is related to the normal module of the gear, which in turn is derived from the maximum torque to be transmitted. Okay. Next slide, please. Yeah, I mentioned about the module. Diametral pitch is 25.4 divided by module. So this curve shows how nominal case depth is related to the diametral pitch uh, for the gear designer. Okay. Now, normally in dimensional aspects, we say there will be a nominal value for a given dimension and there will be a tolerance here. Now, how do we decide tolerance for metallurgical specifications? So, in this case of uh, case depth will have a range, and although I am not showing you that curve right now, but there are curves available, data available as to if there is a range of core hardness, let's say between 25 and 32 for HRC at the root, and then the case depth can be on the higher side of the nominal case depth, which we get from the curve. If it is at the middle range, like 33 to 38, then naturally the case depth can be also kept at near to the nominal value which we get from here. Whereas if core hardness is more than, let's say, 38 to 45 HRC, then the case depth also can be maintained on the lower side of the specification. Rather, specification can be framed in such a way that it will be on the lower side of the nominal value. So like we do it in the case of dimensional aspects, there will be a nominal value. We may decide to give a tolerance on the higher side only or on the lower side only, or we may decide to equally divide it on from the nominal value. Similarly, we do the same thing with the case depth. Okay. Now, this also how much tolerance should be given will be based on the nominal case depth. If it is less than, let's say, 0.4, 0.5 mm, then tolerance is typically 0.1 millimeter. If it is between 0.5 to 0.9, tolerance can be plus minus 0.15 millimeter. If it is more than that, let's say 0.8 to 1.2, typical tolerance is 0.2 or 0.25 millimeter plus minus on the nominal value. And beyond, let's say 1.3, 1.4 millimeter, the tolerance is generally more, either 1.4 or I mean 0.4 or even 0.5 total tolerance. Okay. So next slide, please. Yeah. So next, which is commonly specified in the drawing is core hardness. So here again, what is required is core strength at the root to prevent bending fatigue. And this will be in fact specified in many of the German company standards as UTS only. So many MPa or so many kg per mm square like that. And in other places, although it is specified at core hardness, as we know that hardness and UTS are closely interlinked. So those will be specifically representing the UTS which can be achieved with that core hardness. Now, one other thing is that core hardness has got a major function in the uh, performance of the components or specifically the gears. Many researchers have found that in effect, if we plot a graph of core hardness versus fatigue properties, then it looks like a bimodal distribution. Actually, it is not a bimodal distribution. It is two fatigue versus core hardness curves superimposed upon each other. And the first peak of the first curve is in the region of 35 to 36 HRC, which represents a predominantly magnetic structure, whereas the other peak of the fatigue curve is in the region of 42 to 43 HRC, and that represents predominantly magnetic structure. Okay. So again, that's why today people who earlier specified as wide a band as 27 to 41 HRC or 30 to 43 HRC, most of the people have started specifying either 34 to 42 or 35 to 43 HRC in that range, because it covers both these peaks of the best fatigue performance. So here, this is achieved through combination of correct steel grade and suitable heat treatment. The suitable heat treatment is mainly the quenching. The quenching is you have to select a proper quenchant to achieve proper core hardness as per the requirement based on a certain grade. Whereas the grade specification will be based on what is the requirement of the design. The steel grade should ensure that proper case and core hardness and microstructure should be achieved by non-conventional quenching in oil. Since most gears are oil quenched, the alloy content is important, and the hardenability should be such that it will give proper transformation in the case as well as core. If hardenability of the core is okay, you will get a good core hardness. But case hardenability, which is alloy dependent, you have to consider for getting a good microstructure in the case. We know that we need good microstructure in the case, which we'll be discussing now. Okay, next slide, please. Yeah. So many of the properties and performance of the gear are related to and influenced by microstructure. So in a heat-treated component, UTS is directly proportional to the hardness. It has got good, relation to the hardness at that point. But yield strength, which normally in a good hardened structure, properly hardened structure, will have a relationship with the UTS. The moment you get improper microstructure like presence of ferrite, either blocky ferrite or even distributed ferrite in a greater extent, that will reduce the yield strength. And many of the designs are based on yield strength and not on the UTS. This is because the moment the component starts yielding, then it is no more a good component. The dimensional changes cannot be tolerated in the functioning of the component or running of the component. So that's why this particular factor has to be considered for the heat treatment and controlling the microstructure. The importance of the core hardness is of course there. It broadly gives you idea that the core strength is good. But if the core micro contains a lot of ferrite, then it can fail by case crushing or it can fail by bending fatigue. If the fatigue, this is depending on the location of the ferrite. If at the PCD level, pitch level, you have got ferrite, then the effect will be, the failure will be by case crushing. And if the ferrite is at the root fillet or at the root base, then the bending fatigue strength will be adversely affected and the component will fail by bending fatigue. Next, please. Yeah. We all know that case microstructure needs a good amount of martensite. Now, martensite are of two types. One is a latch type martensite, which has got less than 0.6% carbon. So invariably, core will have some amount of latch martensite at least. And whereas you will find that wherever the carbon percentage is more than 0.6%, then it will be fine structure of parallel twins, that is plate type of martensite. And naturally, what we desire in the case is plate martensite, acicular in nature. Next, please. Yeah. This shows the difference between appearance. This is at almost 400x magnification, and so left side shows lat martensite, and right one shows the plate type martensite. You will find the difference in the microstructure can be easily identified in the under the microscope. Next, please. Yeah. Now, other structures which can appear in case microstructures are retained austenite, carbides, free carbides, decarb, grain boundary oxidation, and non-martensite structures. So we'll go one by one. Next slide. Yeah. Typically, the in a given steel grade, the amount of retained austenite is a function of what is the final surface carbon. Because higher amount of carbon than optimum level of 0.8% tends to stabilize austenite. It depresses the martensitic start and martensitic finish temperatures, and at a point it will go below the surface, below the room temperature. So once that happens, then the transformation will be incomplete, and even after full quenching is over and we take out the components from the bath, there will be some amount of austenite which is untransformed, which we call as retained austenite. So you'll find that first one is a very good microstructure with negligible retained austenite. The second one has got about 10 to 15% austenite. Then third one almost 25%, and fourth one is more than that, around 30 to 35%. Generally, retained austenite under 10% is acceptable in most cases. Uh, but beyond that, it is not acceptable because it gives you a untransformed structure which can transform during the field and cause cracking, because that will generate richly formed martensite because of the mechanical working, and it will be cracking at a later stage. When the structure of the case is coarse, there is a coarse martensite generated which has got micro cracks across the platelets. Okay. And those may not immediately affect the performance, but over a period, those will act as stress raisers under the fluctuating load conditions or stress levels, and they will be starting points for fatigue cracks. So that's why today everybody specifies fine-grained structure so that we do not get coarse martensite. Next slide. Yeah. Uh, there are two major types of carbonizing cycles used. In one case, the components after carbonizing is over is cooled to a lower temperature of hardening for the hardening. It is held for a shorter time to homogenize the temperature, and then it is quenched. This is called the modified direct quench. So this is commonly used because it saves a lot of energy, and it also gives you fairly consistent results. But this has got a tendency to retain austenite if carbon control during carbonizing is not okay. So we have to be very careful in this case to have the carbon control absolutely good. But the second type of cycle is carbonize, cool the component after carbonizing below the critical temperature of 723 to the extent of about 500 to 600, then reheat and then soak and then quench. So this is reheating cycle, which is also used to a lesser extent today, but it's still used. Uh, this tends to reduce the retained austenite drastically, but this also tends to give you some spot carbides finely distributed in the martensitic background. So this is an acceptable structure and gives you excellent properties of the case. And the finely distributed carbides also add to the wear resistance of the case. Next slide. Yeah. So the both austenite and carbides go on increasing with increasing percentage of carbon beyond the eutectoid point, that is 0.8%. But that eutectoid point tends to shift as we change the alloy content. For example, alloying elements like chromium, molybdenum, silicon, they are carbide formers. And so they tend to form carbides if the carbon content of the case is more than the optimum. But if you have got the alloys like nickel or manganese, they are austenite stabilizers. And with those, you will have, with the similar situation of higher carbon, you will tend to have a structure which contains more retained austenite. So here we have got a case which is showing you the effect of uh, carbide forming elements and excess carbon. So in the first case, the structure is fairly good. Second stage is also good. In third case, you'll find along the grain body some spots and small platelets of carbides have started appearing. The fourth one shows distinct formation of carbide platelets along the grain boundaries. Next one has got a fair amount of network carbides, and the last one has got heavy carbides with network. The first two microstructures are generally considered as acceptable. The other four are not considered as acceptable because they weaken the grain boundaries and there will be a flaking off during the uh, alternating stress cycles. Next, please. Next, please. This shows uh, again effect of excess carbon, grossly excessive compared to the optimum carbon of ejectile or 0.8%. So you will find in the upper left you have got a very heavy carbides, although they, to some extent they are disjointed. They are not fully connected. The right upper slide shows you formation of austenite in a greater percentage, as well as formation of carbides in plate form. Then third one shows a complete network of carbides, and this also indicates fair amount of coarse grains which are present there. And fourth one has got a structure which I showed you, which we saw recently in the coarse martensite, where you can see in the platelets itself uh, cracks across the platelets. Next, please. Yeah, this is at higher magnification showing grain boundary network uh, practically fully jointed. And of course, this will be weakening the grain boundaries to a very great extent, causing early pitting or spalling failure. Next, please. Yeah. Decarbonation generally does not occur in carbonizing process as such. But there are specific conditions under which it can take place. There are two major categories of decarbonation. The left slide shows complete decarb. It is fully ferritic layer at the surface. So naturally, this kind of structure is totally unacceptable. The other one has got small patches of, small areas of ferrite which are present there. The typical of these structures happen only in under two conditions. Number one, if there is a failure of control instrumentation, carbon potential controller, then this can happen. The other one, which is more common, is leakage in the furnace from the furnace shell. But most common reason for this kind of microstructure is failure of the jacket or the recirculating fan. We all know that recirculating fan has got two bearings. Upper one is a normal bearing which is outside the shell of the furnace. The lower one is inside. So that tends to get overheated and it can fail quickly. But to keep it running for a longer time, a cooling jacket is provided using either air or water. So if by chance for a period of time the jacket punctures or cracks, then water will go into the furnace and the water vapor is highly decarbing in nature. So the moment you get an indication, this may not happen suddenly. So you have to keep on studying the microstructure batch from batch, and the moment you see some amount of decouple. Immediately we have to take an action to find out why it is happening and correct the situation. Many times you'll have to replace the fan unit totally, or you may have to shut down the furnace and then do the needful. But those are the two conditions under which it can happen. Next, please. Yeah, this is the black plate-like or network-like thing, uh, which you can see in the along the grain boundaries is grain boundary oxidation. Now, in most of the carbonic furnaces, the atmosphere, which is endo-based, is generated by combustion of partial combustion of or cracking of a hydrocarbon like LPG with mixed with air, and so there is some amount of oxygen that is present always, some ppm of oxygen. The steel making involves in the final stage the removal of oxygen by deoxidizing agents. These are typically ferrosilicon and ferromanganese. So uh, those elements have got higher affinity towards oxygen compared to the iron. So they will get preferentially oxidized and they will form slag and float away from the liquid bath. Now, the same, the seal will be quite okay then with reduced content of oxygen. And subsequently, of course, it will also subjected to vacuum degassing and the final deoxidation by either aluminum or vanadium, depending on the type of grade that you are talking of. So under this condition, the steel becomes fine grained and also the oxygen content is reduced to a great extent, reducing the oxide inclusions in the steel. Oxide inclusions are supposed to be responsible for the lowered fatigue life. So that's why this killing by so-called killing by aluminum or vanadium is done in the final stage. But the manganese and silicon both are present in the steel as alloying elements. So these under the gaseous atmosphere which contains oxygen will get preferentially oxidized and they form this kind of carbon network. To some extent, this is unavoidable in an atmosphere where we do not have control of the oxygen to that small level. And that's why we use, in fact, the oxygen probe for control of the carbon potential. Okay, because there is an oxygen in ppm level at least present in the gaseous atmosphere. But this should not exceed about 12 to 15 microns in a typical steel quench furnace. If it is more than that, then there is an issue with the control system or maybe leakage from the somewhere in the furnace chamber. We go to the next. Before we go to the next, one more point. Today, some people have gone in for vacuum carburizing because it doesn't have the oxygen itself. Total air is taken out of the furnace before you start the operation or charge is loaded. So that's why it is almost free from oxygen. And that's why you will not find this kind of GBO, grain boundary oxidation in vacuum furnace. Okay, so next slide. Non-magnetic microstructures which can be seen if the carbonizing process is not properly controlled, especially in the last part of the carbonizing and cooling cycle. The structure that we see has got non-monatomic phases like bainite uh, and also some amount of perlite may be present. Okay. Now, this structure is a result of two aspects. Number one, when you have got grain boundary oxidation, there is a depletion of those allying elements at the surface layer. And if on top of it you have got carbon depletion also because of improper carbon potential control, especially in the last part of the cycle, then the combined effect will be a very greatly reduced hardenability of the surface to the extent of 10 to 20 microns. And so that part will form all sort of non-martensitic structures, even though it is at the surface receiving a very good quench, it will have a non-martensitic layer. So that's why while we cannot fully control the GBO, it is in our hand to control the carbon, surface carbon levels to the last point of just up to the point it goes for quenching. And in some cases, the GBO as well as this kind of uh, microstructure, they may be accepted by some of the components because they are doing either gear grinding or honing. So under those conditions, the design may permit some amount of these phases, but generally, since it is indicative of bad control, it is not recommended at all. Next, please. Yeah. Now we are looking at various gear materials and the treatments given, and what are the results of those. You will find cast iron both used for gears, and even today it is used for some of the gears. Uh, so that has got a fairly low hardness of 200, typically 200 BHN, a very low surface durability, that is pitting resistance because of the low hardness. It may not wear out because of presence of graphite and because it is self-lubricating type. But by pitting and spalling, it will fail early by surface pitting. The maximum contact strength that can be tolerated is 85,000 psi, which is quite low. And the bending strength is quite high because it is rigid in nature. So it is 30,000, which is quite good. The hardened and tempered steel with about 300 BHN hardness will have an improved surface durability and also a reasonable bend contact stress because of the higher hardness, and maximum bending strength is also lower because of the stress that is existing, stress level and stress pattern. We'll come to that slightly later when we discuss the carbonized gear. Next is the steel, which is uh, flame or induction hardened. That can go up to hardness levels of 50-55 HRC. Has got very good surface durability because of the hardness and predominantly microstructures. The bending strength is reasonably good, but it doesn't have the very good, sorry, surface contact strength is very good, but the bending strength is not. In case of nitrated steel, you will find that it contains very high hardness, although we mention it as 60 HRC. The if it is measured on a micro scale, it is equivalent of 68 to 70 HRC also. It can be. So therefore it has got a reasonably good surface durability or contact strength, and because the nitride depth is not very high, you will find that it has improved, but not to the extent of a carbonized beer. Hot-tempered ethyl iron has been used by people like Volkswagen and some of the American auto manufacturers, and it performed well. I personally had developed for Bharat gears the components made out of ADI, and typical hardness measured on BHL was only 450. But the structure was such that it was partly magnetic and partly martensitic. And it had a good contact strength as well as reasonably good bending fatigue. When we come to carbonized hardened and tempered steel gears, then 60 HRC is very common specification and which can be achieved. You'll find that surface deliverability is factor is highest. The contact stress that can be tolerated is also very high, 25,000, and the uh, 300,000, and the bending strength is also highest available among the other materials. As I mentioned in the earlier meeting, surface hardness of 60 HRC corresponds to 300,000 psi surface strength. So, if you take a normally designed normal functional gear, it will have a requirement of only 180,000 or 200,000 psi strength, whereas this is going to 300,000. It is much above that. In fact, most heavily loaded components also, they do not need more than, they are not designed for more than about 240, 250,000 psi. So this is higher than the maximum loaded gear also. So that's why today you'll find close to 75-80% of the gears are put through the last treatment of carbonizing, hardening, and tempering. Next, please. Yeah. So, what are the properties of carbonized gear parts? It is like having a composite with unique combination of properties. High surface hardness to withstand the contact stresses, high wear resistance, low carbon alloy giving tough core to resist shock loading. I must mention that in a typical manual transmission gearbox, the first speed, the reverse gear, and the reverse idler, these three gears are subject to the impact because the vehicle is at standstill when they are coming into operation. Whereas the other gears are already in mesh, the vehicle is moving, so there is no risk of having impact. So that's why when if you look at the specifications for various components, these three gears, first speed, reverse, and reverse idler, these are always specified with a better alloy steel to give the tough core to resist shock loading. Good beam strength derived mainly from the core hardness. Here, the case depth at the root also plays an important role to improve the effect of good core hardness in case of bending fatigue. Adequate surface yield strength to resist case crushing and yield residual compression at the surface, which is very good for improved fatigue. Now, when you change a carbonized component, the core has got a transformation temperature between 200 to 450 degrees Celsius. And whereas case, because of the higher carbon, starts transforming below 200, and many times, as we saw, if carbon is slightly higher also than the optimum level, then it has got a tendency to go, the Martin-Slick finish temperature will go below the AC. But the main thing is core is already transformed when case starts transforming. And core has got a much higher volume and it is already transformed. So it is resisting the high volume change of the case, which is almost 4 times compared to the core. So the tug of war between these two areas of the carbohydrate component leads to a compression, net compressive stress at the surface. And that's why it will not fail unless you have got an external stress which is more than the surface compression. That is the reason why the critical gears are short pin in addition to carburizing to improve the surface compression further and to improve the fatigue life. Next, please. Yeah, the carburizing process uh, depends on 6 main factors. There will be many, but I'm just taking 6 which are really important. Time, which we know that at the time the cases will be higher, but the relationship is very adverse. The penetration of the carbon or carburized case achieved depth of penetration is dependent or proportional to the square root of time. So it is it plays a law of diminishing returns. Whereas next parameter, and it is also very easy to control time. Next one is temperature. Here, it has got a totally different relationship with the penetration or diffusion, depth of diffusion. That is, the depth of diffusion is proportional to the fourth power of absolute temperature. That means if you increase the carburizing temperature a little bit, the depth will go up on a very high scale. At the same time, the control of the process becomes difficult. That's why if you have got shallow cases like 0.2 to 0.5, temperature use will be less, where you can have very good control of the case depth. And then you will go to maybe 900 or 910, or is it between 0.5 to 0.8, and beyond that you can go to 930 or 935 or even higher. So temperature we can use to the advantage for gaining time, reducing the time of process and reducing the cost of the overall operation of carburizing. But of course, you have to also consider the fact that some of the steels and many times some of the components which are delicate in construction, they will have more distortion if you change the carburizing temperature upward. So there's a we have to consider both the aspects together and take a decision. Carbon potential difference is like uh, a voltage in an electrical circuit. For a given resistance, higher the potential difference, higher is the current. So that means if you change the difference between base carbon and the potential in the atmosphere, then the rate of diffusion will go up. Alloy content in the steel is one of the factors that is called an alloy factor or correction factor. We know that 0.8 is supposed to be the optimum uh, carbon for any steel, but it is not strictly true. If you have got a steel like 20 mm CR5, the alloy factor there is 0.9. That means 0.8 multiplied by 0.8, 0.9 multiplied by 0.8 which is 0.72, will be the optimum surface carbon for 20 mm CR5. Whereas for a low alloy steel like F620, okay, where there is no major alloying element present. So there you will find that it can tolerate a carbon final surface carbon of 0.82 to 0.85 also. Uh, Carbon mass transfer coefficient is something to do with the uh, input gas which we are going to use for the processing. For example, if you have got a propane or butane, the typical coefficient, carbon mass transfer coefficient is 1. And compared to that, if you can use acetylene, the availability of carbon is so much, it is capable of giving much more carbon by dissociating or cracking. And so the carbon mass transfer coefficient goes to 1.3. And so you'll have a drastic improvement in the diffusion rate also. These are carbon mass transfer coefficient is basically capability to donate carbon to the steel from by the atmosphere. Circulation of gases. We'll look at it slightly later. Next slide, please. Yeah. The typical carbonic atmosphere will have carbon monoxide, carbon dioxide, hydrogen oxide, that is vapor, nitrogen, and small percentage of methane, which is a transit gas. And there will be small ppm of oxygen, which I have not mentioned here. So at hot steel surface, carbon monoxide decomposes as 2CO plus ion, gives you one nascent carbon and one CO2 is generated and ion remains like. So this is something like that hot metal surface is acting as a catalyst. It is also capable of absorbing carbon. So this normally the carbon by itself cannot penetrate the hot metal, but this nascent carbon is capable of penetrating and causing carbonization. The CO2 then reacts with enriching hydrocarbon gas to form CO again as given below, and thus the reaction continues. And this tells you that for continuation of this cycle of first reaction and second reaction, you have to have a good circulation. Otherwise, in the pockets between the charge, you'll have stagnant gas containing more CO2 and less CO, and so carbonizing potential there will be locally dropping. So dense charges especially uh, are very sensitive to having good circulation. But even normal charges with ample open space at the root fillet and all that, you'll have a problem having a good circulation, and so a good circulating fan continuously running is important. Next, please. Yeah. So type of carbonization cycle, there are many. We'll just discuss the first one, which is important. Next slide, please. Yeah. So many people just go by thumb rule of deciding what carbonization cycle should be used when a new component comes in. It's not totally wrong. They are doing it on the basis of their experience over a few years. But more scientifically, it can be calculated to a greater accuracy, and that can avoid trial and error, and we can have first time right type of operations. The boost diffuse carbonizing cycle using the auto control for the carbon potential and temperature both is used. And the diffusion potential, initially you have during the boost part high potential like 1.15 to 1.2, even higher, or if you are using higher temperatures. So that will ensure that you achieve the first, in the first part itself, sufficient diffusion of carbon up to a greater depth. And in the second part, where in the diffusion, you reduce the potential to between 0.7 to 0.9%, depending on the alloy grade that we discussed. That will give you a final carbon which is optimum to obtain the surface microstructure, surface hardness, and good performance in the field. Now, calculation is based on Harris equation, which is uh, given below. But it is important to understand that what is specified is typically effective case depth measured to a particular hardness. The Harris equation and other equations of diffusion, those laws do not know anything about the hardness. They only know about the carbon penetration or carbon diffusion. So you have to correlate the ECD to the total case depth, which is the carburized depth. And that's why you'll find that if you try to correlate in a conventional oil and a good carburizing cycle, you'll have between 70 to 75% of the ECD as effective case depth. Okay. So if I want a final effective case depth target of 1 millimeter, I'll be targeting total case depth up to 1.25 or even 1.3 millimeter. Okay. So uh, this is the first aspect which we have to consider. And the next important equation is the total case depth is K root T. K is the diffusion coefficient at that temperature, and the T is temperature itself. So you have got the diffusion coefficient, which can be calculated by different means. But the ready data is available in most of the handbooks and various literatures, so we can use it. For example, at 927 or 925, you'll have a K equal to 0.635. What it means is, in 1 hour, it will achieve a total case depth of 0.635 millimeter. Next, please. Yeah. So now if we know that, okay, we will need, let's say, 3 hours to achieve a particular case depth, then we'll have to split it between boost time and diffusion time. Okay. So that is calculated in the, as given in the upper equation. Boost time is equal to total time, and you have got the diffusion CP minus base carbon, which is typically 0.2% in the carbonyl periods, and boost CP minus base carbon, both the bracket is squared. So you'll find that if you calculate this way, giving 1.2 and 0.2, the numerator is 1 and denominator is 0.8 or 0.6, sorry. So you'll have a typical timing of let's say 3 hours or so. And so diffusion time will be the total time minus the boost time. And this is the point which is has to be considered. Boost CP, how do we decide? That is based on the saturation point of austenite with carbon and tendency to form soot. So whereas diffusion CP is governed by the alloy content, which affects the ideal surface carbon required. So for the correction factor for the alloy is given below, but you need not remember that. Next slide shows what are the typical correction factors. Next slide. Yeah, a plain carbon steel like C15 will have a correction factor of 1.02, which means that to achieve final carbon of 0.8, you will have to use 0.8 multiplied by 1.02, slightly higher than the 0.8% carbon. The 16-MnCr5 will have a correction factor of 0.92, 20-MnCr5 0.9, like that. It will change with the increasing alloy typically. Next slide. Yeah. Control of the carbon potential can be done in one of the three methods which are common. Infrared CO2 analyzer has been one of the older system of measurement, and was in the all different gases that are present in the carbonic atmosphere. You control any one, and the others get controlled. Other percentage of the other gases get controlled, because there is, as we saw, there is a chain reaction going on where you are converting CO at the surface, converting it to CO2. CO2 reacts with the enriching gas, again gets converted to CO like that. So it's a dynamic equilibrium that is happening in the furnace gas. And that's why you control anyone which is conveniently convenient for the instrumentation. So CO2 analyzer measures CO, converts it into carbon potential. Similarly, dew point, which is a measure of water vapor content in the furnace gas, and it converts it into carbon potential again. The best and most commonly used is today zirconia oxygen probe, which measures the very small percentage of oxygen. But it is a valuable development, because compared to any of these above methods, the zirconia oxygen probe generates a very high EMF, and that can be, typically it is in excess of 1100 millivolts. So to that extent, even 1 millivolt change will be a very accurate control of the furnace atmosphere. Also, compared to the other methods, it is very convenient to automate, as well as it is very sensitive. So if there is a small difference in the composition of the gas or atmosphere, then immediately it will show up in the millivolts. That's why today you'll find small and big, most of the heat treatment shops, they use the zirconia oxygen probe for control of carbon potential. Next, please. Carbon nitriding is another process which is commonly used for gear heat treatment, and it is a modified carbonizing process with simultaneous addition of ammonia to the atmosphere, which acts as a source of nascent or active nitrogen along with the carbon. Like we saw that normal carbon cannot penetrate the steel surface, but carbon, which is in a nascent form or active form, it can penetrate. Similarly, normal nitrogen, which is present already in the steel gas, it cannot do nitriding or nitrocarbonizing, carbon nitriding. Sorry. But if it is in the cracked form as a nascent nitrogen, it can penetrate. And so simultaneous diffusion of these two elements will occur. And the result is a better wear resistance. It permits use of cheaper grades to achieve similar properties what you would have got with plain carbonizing. The temperatures are typically lower for carbon nitriding, because nitrogen dissociation process or reaction is more at lower temperature, exactly reverse to the carbon generation of nascent carbon from the CO. That increases with the temperature, whereas nitrogen generated from the ammonia gets reduced by increasing the temperature. That's why an optimum temperature of 10 to 870 is commonly used for this. And where do we use carbon nitrogen? Where you need slightly better wear resistance. Like if I have a gear which is going for tractor or earth moving equipment, those are heavier cases. Wisdoms are more. There you need high temperature to have it in the lower time. And it is sufficiently good because the peripheral speeds are also lower, so wear resistance is not an issue. So those gears are invariably carbonized, and whereas if you go for two-wheeler or four-wheeler, the peripheral velocities are higher, and the requirement of torque transmission is relatively lower. So you can afford to have shallow case and therefore go for carbonitriding. The other advantage is because of the lower process temperature, the distortion is less. The noise generated of carbonitrided gear, you will find is invariably lower compared to the carbonized gears which are processed at higher temperature. Next, please. Nitriding is an extension of what we discussed. It can be done with or without previously hardened and tempered conditions depending on the application. Where you need good core properties, those who can be provided by having a pre-hardened and tempered condition. So the gas nitriding can be done or liquid nitriding can be done, or it can be also done in the fluidized bed type of furnaces. And this can be also used for mild steel or carbon steels going up to 2 stages to improve as per the requirement the required properties. For example, nitriding is often done for tool steels, forging dies. If those are nitrided, then you'll have much better hot resistance to thermal fatigue, which is common with the forging dies. Okay. Whereas for other areas, nitriding is done purely for the wear resistance. And here also very low temperature is used, so below the critical temperature. So the nitrided components are not quenched. They need not be quenched. Next, please. It can be done in ferritic but or austenitic condition, but it is commonly done as FNC or ferritic nitrocarbon, which is becoming more and more popular. The reason is that nitrogen element is predominant in this, with very small percentage of carbon addition also. And it can be done in gaseous atmosphere, vacuum or fluidized bed again. The purpose here is different. You can get a few micron layer of which is nitrided, a small layer of the nitride or white layer, followed by a diffusion layer which can be 0.2 or so. The typical nitride layer is between of 8 to 15 or even 20 microns, depending on the application. Many times, this is followed by steam bluing or other thing for increased corrosion resistance, improved surface appearance, like that. Next, this selection of process uh, is depending on the application, as we discussed in case of carburizing and carbonitriding. So, uh, the design considerations as to what kind of stress levels are expected to occur, that will decide what process of case hardening will be used. We come here to the end of the presentation, and you are free to ask questions if you want.
Sandeep, you can now unmute yourself and talk. Sandeep Rege.
Yes, yes. Thank you. Thank you. I was unable to unmute myself. Anyway, thank you. So thank you very much for your nice presentation. Whatever is, it's a whole of heat treatment and whole of carburizing, carbonitriding, and things like that. So basically, why the gears are to be heat treated, and what are the impacts of the gear getting heat treatment, and things like that were nicely explained. So there are a lot of questions from the participants. I would take one by one
Yeah.
so that you can please, yeah. So the first question here is from Somnath. Sir, vacuum carbonitriding is done with higher temperatures up to 950 degrees centigrade. So what's your opinion on it? If you can comment, your comment on it.
Yeah. In vacuum carburizing, the main advantage is you do not have oxygen, so there is no oxidation of the surface. There is not oxidation. Now, this you can increase the temperature uh, beyond 960, also going up to 1010 in the extreme case. The cycle time drastically. That is one of the major advantages.
I think he wanted to ask whether it is 950 is okay, or should we reduce it to 930 or 920? That's, I think,
No, in vacuum
must have
is
been his point.
the main advantage of vacuum is, of course, that you have control over the absolute control on the grain boundary oxidation. But
Yeah.
the other way is there are two aspects of that. Number one is the acetylene is used as a carburizing medium, and acetylene has got very high percentage of carbon, 1 to 1 compared in, if you relate it to the hydrogen present. In any other hydrocarbon you take, C4H10, so you have got 10 atoms of hydrogen to 4 atoms of carbon. So you will find, whereas in acetylene you have got equal number of carbon and hydrogen atoms. So that is a major thing. And that's why the availability of carbon at the steel surface is very high. Now, I forgot to mention that there are two different processes simultaneously happening in carburizing. Number one is donation of carbon to the, or cracking of carburizing medium at the steel surface, and initiating the carbon penetration at the atmosphere and steel surface. The other one is inward diffusion of carbon. Now, if you have got a potent atmosphere which is not capable of giving very high carbon amount of carbon, then raising the temperature of processing does not make sense. Okay.
Okay.
It will cause, in fact, depletion, lowering of the surface carbon because inward diffusion.
Okay.
In this case,
Yeah.
because of the uh, acetylene, you have got a very high carbon donation capability from the gas to the steel surface. So, taking advantage of that, if you raise the temperature, it will increase the diffusion rate in a very advantageous manner, and you can complete the carbonizing part in a very short duration.
So there's another question where are there any disadvantages of carbonitriding over carburizing? So that is one question. Yeah. Any
I think,
disadvantages of carbonitriding?
Sandeep, you should
Yeah.
just wanted to say that, but I'll venture to answer that. Uh, See, there are some metallurgical aspects which have to be considered. For example, people like Fiat, they have got vacuum carburizing and they use 20 MNCR pipe. But there, it is not standard 20 MNCR pipe because vacuum carburizing is followed by gas quenching, which is not as severe or as quick as oil quenching. So, you can improve the thing by having a modified grade which has got carbon content of 27 to 33.77 to 0.33. So, this is one of the things
Carbon.
that you need to whether the hardenability of the material getting heat treated is adequate for the relatively sluggish quench of gas quench. Actually, everybody uses nitrogen, but it is known that if you use hydrogen or helium, the cooling rates are much higher. But people are worried about the handling of the gas because hydrogen, as you know, is uh, explosive and flammable. Nitrogen is neutral, so it is very safe to handle. But the fact is, if you use gas mixture, then you can improve the thing even without much change in the handleability. But with standard gas quenching methods, although you can go for higher pressure gas quenching, the cooling rate cannot be similar to that of oil quenching.
Oil quench.
So that is one aspect to be
Right.
considered. Second thing is the coarsening of the grain coarsening because of the higher temperature. Now,
Hmm.
today most of the steel that comes in has got a fair amount of aluminum and nitrogen, giving you a very fine grained steel. And with when you are trying to reduce the time at carbonizing temperature to a great extent, the coarsening, which is dependent on time and temperature, can be still controlled. So
Okay.
that part, which is typically worry of a heat treater who is conversant, who is not conversant with vacuum, but conversant with conventional processing. For him,
Yeah.
this will be a worry. If I raise the temperature, what happens? Here, you'll not only achieve faster case depth, but because of the reduced time, even at that temperature, the coarsening uh, is not an issue.
Yeah. So there is another question of white layer formation after gas nitriding of H13 tool steel. Is it good for aluminum die casting applications? That is the question from Amit.
See, uh, for specific conditions, no, for many of the dyes, both for forging and the same, the problem is checker cracks due to thermal fatigue. Okay, there is a continuous fluctuation of surface temperature of the dyes, and people try to cool it by some method or the other, but still it cannot be avoided, and therefore the uh, checker cracks because of the thermal fatigue of the surface bound to happen. Now, it is found, and I have personally tried out. I have not tried out for the uh, injection molding or those kind of dyes, but I have successfully used forging dyes for extrusion process, reverse extrusion, in which the hot metal flows over the small sized tool, the mandrel, and that is subjected to very high thermal fluctuation. So there it was found that we got very good life improvement by going to nitriding. Of course, we have done plasma nitriding, but it doesn't make a difference which type of nitriding you use. There is a small amount of white layer there, and it is good for good because the uh, scuffing resistance, the frictional coefficient comes down. That makes it advantageous. In both the conditions, the die casting as well as the forging, like reverse extrusion, the problem is lubrication of the dies. So to an extent, the uh, material flow can be easier because of the reduced scuffing, better scuffing resistance of that layer.
Yeah. So there is I think Murugappa Perumal. Yeah. There is a question which is ECD formula. I think he has explained it in his presentation. So you can go through that formula again. Also, there is a question of, yeah. There is one more question which is Mr. Praveen Kumar. He does EN2 low carbon steel at 930 degrees Celsius. They achieve TCD as 1.2, but ECD they achieve only 0.35. So if you can suggest some methods to achieve ECD to 1 mm, that's the question. EN2 low carbon steel at 930 degrees Celsius.
What was the grade? What is the
He
grade of the
achieves
steel?
TCD as EN2.
Huh? Hello. Which is the steel grade?
EN2. EN series
EN2.
2.
Okay. 2. Okay. So that's a uh, plain carbon steel with very low carbon, and also it has got hardly an alloy content. So there, it will
Yeah.
not be possible to achieve the case depth at the root. Why I'm saying this is there are two aspects of what case depth we are talking of. One is diffused case, and second one is hardened case. Okay. So the diffusion phenomenon is such that at the tip of the gear tooth, you have got penetration occurring from two sides. So this geometrical factor reduces or increases the penetration at the tip of the component and at the top land. It, at the PCD level, it is much lower than that, and at root, it is even more less, because there the risk of stagnation of this thing is also less, plus the gas volume there available is less, and more volume of the material which is sucking away the carbon diffused into the surface layer is there. So it is a reverse of tip portion where you have got three sides allowing the carbon penetration into the metal, and inside there is very little volume available for the diffusion. So there the potential effectively is more and you get good diffuse case. The second part is for getting effective case, you need hardenability. So only if you have got a good alloy steel, you will have lesser difference between the PCD and root.
Yeah. Rightly said, sir. There are a lot of questions. We will try and pose it to you in writing, but I'll take last two, three questions. One is by Santosh
Okay.
Thapar, a Thapar of BGL. My question is, his question is how to control austenitic grain size 5 or finer in case hardening. How to control the this thing. K,
Huh.
yeah.
For this problem comes up only for deeper cases, like going beyond 1.5 millimeter, because you have got higher time and at temperature. So that tends to coarsen the grain size. But and that's why it is important to have uh, aluminum nitride in substantial percentage, typically 0.02% uh, acid soluble aluminum has to be there. And equivalent nitrogen of about 85 to 90 ppm that must be present to have enough of aluminum nitrides present. And so each aluminum nitride particle is giving rise to one grain or one crystal during solidification. So it will give you substantially fine grain size. Okay. There are two aspects of grain size. This aluminum nitride provides for initially fine grained steel, but there are some aluminum nitride particles which also uh, are present at the grain boundaries. And these provide for a so-called pegging effect. It provides something like a compound to the piece of land, whereby protect the land. So grain size, if you have got good amount of uh, aluminum nitride, then you will have no worry about higher austenitic grain size. I will give you an example. Way back in '83, when at Bharat Gears I was developing gears for uh, Suzuki, Maruti Suzuki. They had just forwarded the specification, and I looked at the steel grade, which was SAM420, and they had specified the oxygen content and hardenability and all that. I looked at that and specified for the steel mill and the forger aluminum content of 0 to 0 to 0.35%. And along with Indian steel mills, we sent it to Japanese steel mills. Indian steel mills accepted. The Japanese steel mill, who was supplier to Suzuki, they said we cannot supply to this. I asked them why. They said for we have developed this steel grade for Suzuki, and it contains aluminum to the extent of 0.45 to 0.55. So ultra fine grain steel, and that's why they added moly, which was uh, compensating for the lowering of the hardenability due to very fine grain. So, but
So there are so many questions.
for normal operations, I will say, see, theoretically, even 0.15 or 0.16% aluminum is supposed to be okay. But I have frequently seen that if you have got aluminum content of somewhere around 0.15, actual aluminum available as aluminum nitride is only 80% of that. So it is in the region of 0.11, 0.13 like that, and that is not good. In fact, a coarse grained steel there will be better than the steel which comes out of this marginal aluminum content, because you'll have so-called duplex grains. You'll have grains which are 7, STM 7 or 8, and in between you have very coarse grains going down to 3, STM 3 or 4. And during heating, you will find that these coarse grain, they will grow very fast at the cost of adjoining fine grains. So not only the grain size will be bad, the resultant properties will be bad, but also it will cause uncontrollable distortion.
Yeah. Sir, there
I
are
hope I have.
still some more questions. What I would suggest is, so we'll take only one last question, and then what we will do is we will write down some questions to you. Maybe you can thereafter at your leisure you can give some answers, and we will try and post those to the participants so that it's already 9:10. So there's one last question from Mr. Prakash. They are getting carbides and high retained austenite at gear tip and tip corner of gear. They reduce their boost CP from point to 0.9 and diffusion to 0.69 at 930 degrees centigrade, but still it exists. Now he's not talking of any steel which originated. So that's his question. But yeah, if you can answer, but he has not talked of any steel which he is using.
Okay. Uh,
Hello.
if you calculate, hello, if you
Yeah.
calculate the cycle as per formally given, there will be only, you will not have to worry about carbides for retained oxide because you are going to maintain the final carbon. Okay.
Yeah.
But this is a mistake which most of the people make. They reduce the boost carbonation potential, which increases the time unnecessarily, and they do not adjust the diffusion potential. Final structure is going to be dependent on diffusion time and diffusion potential. Okay. So if those are taken care of, then you cannot have, it is not possible to get any, because you will have optimum carbon all over.
Okay, sir. Thank you very much. We will try and post these questions to. There are so many still. We will try and post them to you by. We will post it to you on WhatsApp, where you can take your time and at your leisure you can answer those, and we will repost them to the participants so that all are benefited. So thank you very much, sir, for your nice presentation. And at the last minute request, you could help us out in this uh, by taking this technical lecture. So thank you very much, and thank you very much to all the participants from here, from Mumbai. Thank you very much, sir, again
Sandeep, I
Thank
have one
you,
request for
Sandeep.
Mr. Kulkarni.
encouraging us with your nice lecture. I know that you are always there for us here, for entertaining. So thank you very much, sir, and thank you very much, all participants.
Sandeep, I'll take 1 minute. Sandeep, I'll take 1 minute.
Hello.
I must thank both of you.
Hello.
Yeah. Hello.
Hello.
Hello. I'm online.
हाँ सुधाकर जी बोलिए ना.
Ani.
Hello.
Kulkarni sir, I have one small request for you. See,
Yeah.
today's webinar was very excellent, but we want more of your knowledge sharing, and we would like to have 1-day course. Sandeep, of course, will coordinate with you. So I think you should be available to us. That is our request
Okay.
now for 1-day course.
Okay.
Whenever the lockdown is over, we'll have the physical course, not a virtual course.
Okay. You were not there earlier, but let me tell you that my initial almost 15 or 20 years were with India chapter as a member.
Yeah.
and I was a regular visitor as a member as well as a contributor to the various programs. And only when I shifted to Pune after leaving Bharat Gears, I shifted my membership to Pune chapter.
Okay, no problem, no problem. Sandeep will be in touch with you, but we definitely would like to have that. Okay.
Okay.
Thank you.
Thank you.
Okay.
Thank you all.